So let's do a quick recap of what we were doing last week. So we started with the transient 2D heat conduction problem. So the only difference between this one and what we were discussing before this was an extra added spatial dimension. The first technique we discussed was the explicit technique, which is quite straightforward, very similar to what was there in one spatial dimension. So there's not much to discuss because you can explicitly write the unknown as a function of known values, even though the unknowns are now on a two-dimensional grid. So at n plus 1th time you will have more unknowns than you had in one dimension. So you will have a total of, let's say, n times m unknowns in this case, but that's all right because you can still write each and every one of those at the next time step explicitly in terms of the known values at the previous time step. The next was that because of the stability constraints that we have, we may want to implement an implicit technique, that is a fully implicit one would be backward time center space. While implementing that, what we noticed was that if you try to write everything in terms of a vector of unknowns, you get a banded matrix. The issue with that matrix is when you try to solve it using, let's say, Gaussian elimination, the method is not as efficient as it was for one spatial dimension, because between the two bands you have lots of zeros to start with. But when you apply the Gaussian elimination algorithm, then these zeros between the two bands become non-zeros, because they'll be operations on those terms. So that will result in a dense matrix coming from a sparse matrix. So because of those calculations that you have to do to convert those zero terms to non-zeros, the Gaussian elimination method becomes expensive, right? So the next technique, which actually is used in most of the CFD solvers in open source as well as commercial software, and this is beyond CFD, because iterative methods are used to solve linear systems, Ax equal to b, system of linear equations, and you tend to get system of linear equations in fields beyond CFD as well. So this is a very common numerical technique discussed in almost all numerical courses. So in iterative methods, what we do is we kind of discussed the idea of the technique and then stopped there. So the idea of the iterative methods, any kind of method, is that you start with a guess, an initial guess, anything, I mean it could be any guess, and then you improve upon that based on some formula. So if depending on what sort of equations you are dealing with, you will have a formula to improve the guess, and you keep doing this improvement, incremental improvement again and again. That's the reason it's called an iterative technique. You iterate, you keep doing it until you get a convergence, that is you reach the exact or the actual solution to the linear equation. So it's like let's say, I mean it's not exactly the same, but it's sort of you're trying to reach the bottom of a hill. You may have heard of the gradient descent algorithm. So you start with one point and then you incrementally move in the direction of the maximum gradient, negative downwards, until you reach the bottom, and that's typically how you would reach a valley. So this is a similar technique where you iteratively apply some sort of an algorithm until you get convergence, or convergence basically means that you reach the actual solution to the problem. So today we will discuss the actual algorithm and also discuss under what conditions that algorithm will actually reach the exact solution, because it may happen that you may end up going to a point which is not the solution, right? So we'll have to figure out under what conditions will the algorithm converge, and how will we check whether the algorithm has converged. So the convergence criteria is also that something we'll discuss today. So, to discuss the iterative methods, I will write a matrix system, but actually you will not need to write the matrix system Ax equal to B, but we will do that because we want to discuss the methods and its convergence. So, let us write the equations first. Right. So, if I had to write this as a linear system, we will have a matrix which will have n rows and n columns. Right. So, this is our linear system where a11 all the way to ann are the coefficients and x1 to xn are the unknowns written as the x vector, and b1 to bn are the instead of b vector or the right hand side vector. I could also have written it as r. I think last time I wrote it as r, this time it is b, but that is the same thing, it is the right hand side known vector. So, let us write the algorithm of one iterative method, the simplest one, it is called the Jacobi method, and then I will discuss the algorithm with you post that. So, in general the algorithm of most of the techniques will be quite similar except some minor change. So, this algorithm will sort of work for us even for other iterative techniques as well. I will give you tell you what the exact difference is between another technique and this technique. So, the first step is to make an initial guess, okay, because we have to solve for these unknowns x1 to xn. So, we start with some guess values, they could be all zeros, you could assume that all x1 to xn are zeros to start with, and then we will improve it. So, you have to start with some initial guess. Now, with experience you will realize that you will start making a more useful or a better initial guess. So, that will result in a quicker convergence. So, if you have some sort of a feel based on mathematical or physical ideas, you could start with a better initial guess. Okay. So, we will make an initial guess for the x vector, which is values x1 to xn, and we will call this x old. because the whole idea of iterative technique is you have some initial or some starting guess and then you improve it, and then you keep doing that. So you have to start with something and then improve it. So that something that you start with, we'll call it x vector old, and the one that we improve and get as an improvement, we'll call it x new. So we are trying to find x new as a function of x old. So next step would be to find the x new vector, which basically x new vector is new values for all the x values from x1 to xn. So the first, the new value for x1 is written as this expression. So let's try to understand what we have here. If we look at the first equation that I wrote in the beginning of this lecture, that's the equation a11 x1 plus a12 x2 all the way to a1n xn equal to b1. What I have done is I have moved all these terms to the right hand side and calculated the value of x1 using the old values for x2 all the way to xn. That this summation is nothing but the same thing. It's a summation of j going from 2 to n. So one way to write that is j going from 1 to n, and but j is not equal to 1. So that means the summation is from j equal to 2 to n. So what we do is we use the first equation to find the value of x1. Okay. The only difference is now that we are trying to find x1, the new value of x1, but on the right hand side we will be using old values of x2 to xn. So this gives us a way to calculate an improvement. Now I'm just telling you the algorithm. I have not discussed is this a good algorithm, is this a bad algorithm. This works for now. Let's take it that it works, but we'll discuss later under what conditions will an algorithm work, or under what conditions could it fail. Is that clear? Similarly, I could write x2, the new value of x2. So the idea is that to calculate x2, I will be using the second equation. So what I do is, except the term a2 to x2, I move everything to the right hand side, and whatever is on the right hand side, I use the old values of x. So once we have completed this step where we have calculated the new values for x1 all the way to xn, well, the iteration is done, right? So that's the end of the iteration. Any questions? No, this is only one iteration. So the question is that after I have done step number 2, have we got the actual solution? No. So I am still in the process of writing the algorithm. So this is one step in the algorithm. So once we have taken a sweep over all the x values, then the next step is to somehow check if we have converged, because if you have converged you have to stop, but if you have not converged then you have to repeat the steps. Okay. So we will define error epsilon p as the difference between the new value for the pth x and the old value. Okay. So for instance, we have calculated x2 new and we also had x2 old. We will take a difference of those and we will do it for each value. There are different ways to find the error. I am just giving you one method. So you find the error and then check if epsilon p is less than some specified tolerance value. That tolerance value we have to specify. It could be 0.01, 0.001, whatever we want. So that depends on how accurate you want the solution to be. So we will check it if epsilon p is less than epsilon tolerance for all p values. That is for p equal to 1 all the way to p equal to n. To make sure that all errors are small. That is a very restrictive condition, that you have to make sure that every difference is small. There are different ways, as I will discuss later, to check for convergence. This is just one method which is actually quite strict. So this gives you quite an accurate solution if epsilon tolerance is small enough. So once you have checked, so if this is true then you stop, if not then you continue. So I will write this condition in a different way. If epsilon p is greater than epsilon tolerance for any p, so if any of the errors is large, then you repeat the steps, then you make x old equal to x new. So basically whatever new values that we have found, we will make them old values and then we will go back to step number 2, which is to calculate the new values. So basically we keep repeating the steps until all the epsilons become small enough and then you stop. Is that clear? A very straightforward technique. I mean, you would do any iterative technique in like this only. Okay. So this is called the Jacobi method. So the first step that we have, step number 1 is called to give a starting guess. Okay, the second step is called sweep. You sweep through all the points. That's this. Step number 2 is one sweep. Okay, one complete sweep will result in calculating x new for all the values of p values from 1 to n. Step number 3, this is called the tolerance or convergence check, or check for convergence. And this repeating steps 2 and 3, these are called iterations. So one iteration will involve n sweeps. Okay. So actually this is sweeps. Okay. I won't call it one sweep, we will call it n sweeps through n. So you will have multiple iterations, and each iteration will involve complete sweep or n sweeps. Okay. So when you are writing loops, you have a loop inside a loop. So you have one loop for the iterations, and there is another loop inside it for sweeping all the points 1 to n. So Jacobi method is the most straightforward method, but it is slow. The only problem with this is it's quite slow. So we have an improved method called a Gauss Seidel method. So the difference between Gauss Seidel and Jacobi is that in step number 2, when you are calculating the new values of x, so let's discuss it first and then write it. So if you look at the second equation, so while we are calculating the value of x2, because second equation is used to calculate the value of x2, right, the new value of x2, but we already have calculated the new value for x1. So we have sort of an updated value of x1, a better value for x1. So rather than using an old value of x1 in the second equation, it's better intuitively to use the latest value of x1, which is x1 new. Similarly, if you are calculating xp in the pth equation, it makes sense to use new values of x1 to xp minus 1, and then since beyond p, that is p plus 1 to n, you only have old values available, you use them. So basically it's actually much easier to implement this on a computer, because you only keep the latest values, okay, or you only work with the latest values while writing the loop. So I'll only write the difference, I won't write the complete algorithm. It's the same except step number 2. Right, so that's the only difference. Is this difference clear? Yes. Vishal, can you switch off the fan? It's difficult to hear. Switch off all the fans. Louder, please. Less number of variables. Yes, yeah. The time complexity, time complexity will not be different. Time complexity is based on the number of steps you carry out in a given iteration, okay. But what happens is you have a numerical method to reach the final solution. So what we notice here is that if we use updated values of x1, what happens is if you go from one iteration to the next one, Gauss Seidel gets much closer to the actual solution than Jacobi. So Jacobi is also going from one step to the other. Each iteration will involve the same number of calculations, but the number of iterations will reduce in Gauss Seidel. Okay, it's like you have to go from step A to step B, and each iteration involves n sweeps, but Gauss Seidel will make bigger steps and Jacobi will make smaller steps. It's like Jacobi is taking baby steps and Gauss Seidel will take larger steps, but each step involves the same number of calculations. So time complexity of the algorithm in a way is better because you are taking less iterations, but if you take the number of calculations per iteration, that is the same. Oh yeah, sorry for that. Yeah, thanks. It's the pth equation, so we have BP. So what we notice is that Gauss Seidel is usually twice as fast as Jacobi. So what I'll do is step number 2, I'll write it in a different way. I'll multiply both sides by APP just for the work that I'll be doing now. So we'll call this equation A. And since an iteration is basically improving upon the old value, so we can write an iteration as the new value for xp is some incremental improvement on the old value. So you were at some xp old and then now you have an xp new. So you have made an incremental improvement to x. So that improvement or the error, whatever you want to call it, is xp prime. So we typically call it a correction. So while analyzing these kind of iterative numerical techniques, we say that we have a correction x prime that when added to x old gives us the new x. And remember, this is for one iteration. So in this analysis, we'll call this equation B. So let's multiply B by APP. And we use equation A in B. Right, so we have simply multiplied B by APP, and when I use A, well, so A was, so we use the right hand side of A in place of the left hand side of the expression that we have. So APP times XP new is BP minus summation J1 to P minus 1, the updated new values, and then we have summation going from J equal to P plus 1 to N, the old values. right? And now what I will do is I will move this term to the left hand side. That allows me to write the expression for xp prime. So, I am trying to calculate the correction here for this Gauss Seidel method. So, this gets absorbed in the summation. So, in the summation, the second summation which was on the old values goes from j equal to p to n. So, this is the expression for the correction. Just a different way to write things. I mean, I have not done anything new. I have just written. Earlier, we are writing the expression for xp new. Now, I have used some algebra to write the expression for xp prime. So, I can summarize my method as my iterative technique as the new guess for the pth term is the old guess for the pth term plus the correction, and this correction is this term in the square brackets, which is actually called the residual. So, we call it Rp. Which is the residual of the pth equation. So, we will call it Rp upon APP. So, typically step number 2 in the iterative technique for different methods, this is Gauss Seidel, it could be a different technique, is written as xp new is xp old plus Rp upon APP. The only difference would be the expression for Rp. Now, Rp is called residual. The word residual means something that is remaining, right. So, what you see here is, if you look at the term for the residual, it's for the pth equation, it's the right hand side Bp minus the left hand side. So, let us look at the residual expression. So, the pth equation was AP1 x1 plus AP2 x2, then APP xp, and then we had APN xn, and this is equal to BP. So, if I take everything that is on the left hand side to the right hand side, it should ideally give me a 0 if I had the exact correct solution to the equation, but I have not reached there yet. So, using the latest values of whatever x values I have, so for when I am dealing with the pth equation, for the terms x1 to xp minus 1, I have the improved values, the new values, because I have been through those steps. And for the terms xp to xn, I have the old values. So, I use whatever latest values I have, I substitute them in the equation, I take the difference of the right hand side and the left hand side, I get a residual. So, if I have the correct solution, if I have reached the exact solution to the problem, or if you have the exact solution, then the residual should be 0. Okay. So, this is another way to write the equation, and that kind of makes sense because you have A equal to B, left hand side equal to right hand side. If you do not have the exact solution, then they will not be equal, and the difference between the two would be the residual. Okay. Is that clear? Louder, please. This one, yeah. Right. So if you see this intermediate step that we have here, earlier we are writing the expression for xp new. Now we are writing the expression for xp prime, the correction. So in this step, this step that we have here, we took this term app xp old on the left hand side. So that resulted in the summation going from j equal to p to n. So that one term that was added for the pth term. Okay. So the difference is now we are writing the correction expression, not the new x. Right. So if I gave you a question to write the residual expression for Jacobi method, I am sure you will be able to write it. Okay, so please try to write it yourself. And for those who have actually used ANSYS Fluent, that's one very popular commercial software for solving fluid mechanics CFD problems. When you run the code, while it's running, it will plot some graph. That graph is nothing but the value of residual versus iteration. And I have noticed that many a times while we ask this question to those who are doing research, and we ask them that what is happening here, they say the value of residual is going down, so it's converging. Well, that is right, but what exactly is the residual and what is the meaning of iterations should be clear. Okay, so I guess it's clear to you now. So iteration is you are trying to solve the solution or get a solution to this linear system Ax equal to b, and to solve that linear system you don't want to invert the matrix A because that's very expensive computationally. So we use iterative techniques, and each iteration is taking us closer to the solution of that equation Ax equal to b. Okay. So residual is this Rp value. It's not the x prime, it's not the correction, it's not the error, it's the residual. So residual is different from xp new minus xp old or xp prime. Correction is a different thing. Residual, the only difference is basically residual is app times xp prime. It's not converging. Ideally, in a iterative technique, your residual should be showing a behavior where it goes down with iterations. Well, the method that you are implementing is not correct. I mean, see, one major thing in CFD that people deal with on a daily basis is that residual does not go down. That's our daily problem for those who work in CFD. There are many reasons possible. The problem is not well posed. You have you're taking values of, let's say, you're implementing a non-linear problem where you're taking a very large jump between time steps and so on. So there could be many reasons. That's sort of a daily life of a CFD engineer. There's no one answer to it, but that's a question that's people are dealing on a daily basis.
सर जो हमने दो मेथड डिस्कस किए हैं, इसमें हमारा रेजिडुअल जो इंक्रीज नहीं कर सकता क्योंकि हम ओल्ड वैल्यू से या तो उसको अपडेट कर रहे हैं क्योंकि वो कम हो रहा है इसलिए, अदरवाइज हम उसको अपडेट नहीं कर रहे.
No, we are updating. I mean, it's not that we don't know it's getting smaller. That is what I'll discuss now. So what are the conditions under which an iterative technique will converge? Okay, so convergence means residuals are going down with iterations. It's a very good question to think about it, that residuals should go down with time. So in these methods that I have talked about, Jacobi and Gauss Seidel, they do go down with time, but under certain conditions that we will discuss now. Right, so this was a discussion on iterative techniques for solving Ax equal to b. But let us go back to our backward time center space, because we started the discussion with solving that equation, backward time center space for theta, the temperatures. So let us have a quick look at the equation that we are dealing with. So this was the equation. So we had written in terms of the numerical Fourier number gamma, and you have gamma x and gamma y, because now you have delta x and delta y, that is steps in different directions could be different step size. Okay, so this is the equation that we have. So we have sorry, not this one, we will go back to the one where we had I comma j, this one in double index. So that's one good thing about iterative techniques, is that you don't need to write things in terms of single index. You can work with double or triple index depending on the number of spatial dimensions you have in your problem. So that makes it more intuitive to work with. Okay, so theta I comma j is the I comma jth point in your grid. So the n plus 1th value has a coefficient 1 plus 2 gamma x plus 2 gamma y, and then the left and bottom, and you had a right and top. So the stencil of the scheme looked like this. It's like a plus. So you have a center term, then you have left, right, bottom and top. On the right hand side you have theta and I comma j. So we will be using the same indexing and then use the iterative technique to solve this equation. So this is the algorithm of the backward time center space using Gauss Seidel method. It's very similar except that you have different time steps. So we notice that while trying to calculate theta n plus 1 from theta n values, we got a linear system to solve. To solve the linear system, we use the iterative technique. So step number 2 is those iterations, and you keep doing A to D in step number 2 until you get the solution for the theta for that time step. And then in step number 3 you repeat time steps until you get the time that you want to reach. So if you want to reach t equal to, let's say, t1, then you would do lots of time steps until you reach that time. Okay. So please try to think about it. So till now what we are discussing was that actually in the next lecture I will discuss more about the boundary points, but a sweep involves sweeping all the interior points using the iterative technique, and we also may have to deal with boundary points. Well, they may not, I mean, you may not have specified Dirichlet boundary condition. If Dirichlet is there, then it's fine, you don't have to do anything, because that's the value of theta is specified at all the boundaries. But if you have a Neumann or a Robin boundary condition, then you have equations. For example, you may have to use backward difference, forward difference for the boundaries. Then for that you will also have to include them in the sweeps, because at every step you have to calculate the boundary values as well using interior values. So we will discuss that in more detail. Actually that can make or break the problem depending on how you deal with the boundary in these kind of issues. So I will have a dedicated discussion on boundary next time. Right. So if I had to write a loop, sort of a summary here. So in this technique you have time steps. In the time steps you have iterations, and in each iteration you have sweeps. The sweeps involve interior and boundary points, and you keep, so you have lots of sweeps inside an iteration, you have lots of iterations inside a time step, and your actual program will have lots of time steps to work with. So you have a loop inside a loop inside a loop. So things can go wrong in many different ways. So we'll have a dedicated lab on this for you to work with these. Any questions? Okay. So we'll stop now.